So what's up guys, this is me again, your resident chemistry tutor Mark, and welcome to the part 2 of our mini video series for chemical kinetics. Now, for this video, we will be discussing about the rate law and the integrated rate law, or in my personal opinion, I'll call it ano na lang. I also call it, in my personal opinion, I also call it the expanded rate law, since this is since the integrated rate law is more of a deeper examination or a deeper explanation of the rate law. Anyway, so we have discussed in the part 1 of this video series that the rate of the reaction is dependent on the concentration of the reactants. As the rate of the reaction, as the reactant concentration increases, so does the rate. Now, the rate law gives a more quantitative aspect of that property, of that factor. So here, we have a hypothetical reaction here. We are given a hypothetical reaction wherein A and B are your reactants and C and D are your products, obviously. So the rate is directly proportional, as I've said in the part 1 of our video series, is directly proportional to the initial concentrations of the reactants and of two reactants raised to the respective exponents denoted as M and N, M for A and N for B respectively. So in order to make this a full-blown equation, we insert a constant here, which is K. And now let's examine the properties of our rate law. So rate law obviously has a constant. So by definition of constants, they are intensive properties. That means they do not depend on the amount of the substance, or in this particular case, the initial concentrations of your reactants. They depend, however, on the temperature of the reaction. So that is why it is really important that when you're conducting experiments regarding reaction kinetics or chemical kinetics, you really need to maintain the temperature of your reaction at a constant value, whatever value that you're whatever value it is, that you're trying to examine the reaction into or with. So then another is the exponents, and the exponents for each of the reactants, and that is what we call the reaction order. So it's some sort of a qualitative standard that shows how greatly the initial concentrations of the reactant or the reactant in general affects the rate of the reaction. So let's say we give this exponents here value. So for M, let's say this is 1. Okay, forgive me guys, I don't have a stylus. I'm just using my mouse to draw this. And let's say N, this is 2. So, in words, the reaction order is, the order of the reaction is in the first order in A, since the exponent of A here is 1, and second order in B, since the exponent of B here is 2. Now, the overall of the reaction is the summation of these two exponents, or all of the exponents in the rate law. So 1 plus 2, that is 3. That means the overall rate of the reaction is 3. That means the reaction is in the third order, or it is a third order reaction. Okay, forgive my penmanship. It's not its best since I'm not using a pen or anything for this in writing this. Anyway, so how do we know the rate law of a reaction. So we don't unlike gases, we don't use any assumptions, we don't use any equations to determine. You have to find it out experimentally. So how? So what they usually do, not only in the rate law determination but in reaction kinetics in general, is that you have you conduct a series of experiments for that particular reaction. Now, what you do is you hold all factors constant except for one reactant. So that includes the concentration of the other reactants that you don't want to study. Then you determine the rate of the reaction. It's not as easy as it sounds. It's not as easy as it sounds, by the way, because you'll need really special equipment to determine here, which I will not tackle because I believe that is not the scope of this, not only of this video, but also the scope of this topic, general chemistry wise. Okay, so we have here, in experiments 1 to 3, we have here this reaction rather, and in the first 3 experiments, the initial concentration of your nitrite was held constant, all factors held constant, including the temperature, and the initial concentration of your nitrate ion. What is varied is the initial concentration of your ammonium ion. So you have this right here. Now for experiments 4 to 6, it is the initial concentration of your ammonium ion that was held constant, and obviously the temperature. Then you vary the initial concentration of your nitrite ion. Now let's examine experiments 1 and 2. Now if you notice, from experiment 1 to experiment 2, the initial concentration of your ammonium cation was increased from 0.01 from 0.0100 to 0.0200. So that means you doubled the initial concentration of your ammonium cation. Now, if you notice here, what happens to the rate? The rate also increased, but by how much? So from 5.4 times 10 to the negative 7, it increased into 1.08 times 10 to the negative 6 molars per second, or moles per liter second. So you want to know by how much? So it's just simple. You just divide the rate for experiment 2 with the rate of the experiment 1, and you'll get the ratio. So it was found out that, or if you want to confirm, you can use your calculator. It was found out that the rate of the reaction also doubled when the initial concentration of your ammonium ion was doubled. So in experiments 1 and 2, the rate was increased by a factor of 2. The rate is increased by a factor of 2 when the initial concentration of your ammonium ion was also increased by the same factor. Now examine experiments 1 and 3. So again, we have this rate here for experiments 1. Notice that we increase it fourfold, the initial concentration of your ammonium cation. We increase it fourfold. So what happens to the rate? The rate also increased fourfold. It increased by the same magnitude. Then now we look at now compare experiments 4 and 5. Now obviously we cannot compare experiments 3 and 4 since they vary in the concentration of both reactants. We cannot draw any concrete we cannot draw any substantial conclusion from that. Anyway, let's check experiments number 4 and 5. So again, as I've stated earlier, the initial concentration of your ammonium ion was held constant. However, in here, the initial concentrations of your nitrate was doubled from 0.0202 to 0.0404. What happens is the reaction also doubled. It increased by the same magnitude or the same factor. Now, for experiments 4, comparing it to experiment 6, the rate increased by a factor of 4 when you increased the initial nitrite concentration from 0.0202 to 0.0808 by a factor of 4 as well. So from the data that was gathered here, well, thanks to Brown and Limay for providing this data, the initial concentration, the rate increases at the same magnitude when you increase the rate, when you increase the initial concentration of your ammonium cation with by a certain magnitude or certain factor, the rate also increases by that same magnitude or factor. The same is observed with the nitrite cation. So combining these two relations that we have obtained, so we can say that the rate is both affected by the initial concentration of the two reactants in our reaction here. Insert a constant, and the rate law will be this one here. That will be our rate law. So the rate of this reaction, the order of this reaction is first order in ammonium and first order in nitrate. Thus, the overall rate of the reaction is, since 1 is plus 1, 2. So the reaction is a second order reaction. Now let's put our knowledge that we have gained so far to the test. Now we have this reaction here, the reaction of nitrogen monoxide with hydrogen gas to form nitrogen gas and water. So the rate is shown here. Now, if we double the concentration of nitrogen monoxide, what will happen to the rate? Will it quadruple, double, or remain the same? Now, since the nitrogen monoxide is here in the rate law, that means it affects the rate of the reaction. Thus, when you increase the concentration of your nitrogen monoxide, the reaction will not remain the same. The rate will not remain the same. However, since this is raised into 2, now when you double the concentration of your nitrogen monoxide, so you increase it by a factor of 2. Since this is squared, that means when you increase by a factor of 2, the rate will increase by a factor of 2 raised to the power of 2, or 2 squared. So the rate will increase by a factor of 4. So since 2 squared is equals to 4, thus the rate will be quadrupled. Okay? Now let's have this one here. The iodide ion reacts with hypochlorite ion, which is the active ingredient in chlorine bleaches, in this reaction shown here. So we have this data. We have this set of data. Now, from this data, we would like to determine A, the rate law, and the rate constant of the reaction, and B, the rate when the initial concentration of your hypochlorite is this value, and the initial concentration of your iodide is this value. Okay. Now let's let's examine our let's examine our data first. Now let's say that this set of data here, these are one set of data, the same rows, one set of data na sila nga palariha nga conducted on the same that collected on the same experiment. Now let's say this data here. Now let's say this data here is let's call this experiment 1. Row 2 we'll call it experiment 2. Data in row 3 we'll call it experiment 3. Okay. So what do you do to determine the rate law? We also apply what we have learned in the reaction between the ammonium cation and nitrite anion that I have shown in the example. So you compare those. You compare experiments whose initial reaction, wherein one of the reactant's initial concentration is similar. So let's have experiments 1 and 2, since they have the same initial concentration of your iodine, or iodide rather. So that means ginvary lang ang initial concentration sang hypochlorite. Now if you notice, from 0.0015 in experiment 1, it's doubled to 0.0030 in experiment 2. Now the rate, what happened? It increased from 1.36 to 2.72 times 10 to the negative 4. So okay. So how do we get the ratio from there? So simple. You just divide. You have the ratio. Oh no, it's stuck. Okay. Wait lang guys, I'll fix my camera. I'll be right back. So we'll compare the rates of experiment 2 with that of the rate for experiment 1. So if you remember, I'll show it again. It's there. It is 1.36 times 10. For experiment 1, the rate was 1.36 times 10 to the 4th. And for experiment 2, it's 2.72. Wait lang guys. It's 2.72 times 10 to the 4th. So we'll write it down. So we'll write it down here. It's 2.72 times 10 to the negative 4 divided by 1.36 times 10 to the negative 4. So you get the factor, it's obviously 2. So the reaction increased by the same magnitude when you increase the initial concentration of your hypochlorite by a factor of 2. So let's try writing the rate law here. So rate is equals to, we have the rate constant, we insert the rate constant. So since we only have 3 sets of data, we'll just draw the conclusion from there. So that means since the rate increased the same magnitude as the increase in the hypochlorite concentration, that means the rate is first order. The reaction is first order with respect to hypochlorite. Since we don't put exponent ng 1, so it just stays that way. That we're not done yet. We'll now examine if the effects of the initial concentration of your iodide. So here we compare naman experiments 1 and 3, since they have both the same initial concentration of your hypochlorite. Now compare it with the initial concentration of your iodide. It also increased. It was doubled by it was doubled from 0.0015 to 0.0030 moles per liter. Now the rate also doubled by the same factor that we have shown previously. Thus, iodide will also affect the rate of the reaction, since it affects the increase of the iodide concentration increase the rate of the reaction at the same magnitude by the same magnitude. Therefore, the order of the reaction is first order in iodide. Therefore, the rate law of our reaction is this one. And the overall order of the reaction is 1 plus 1. So this is a second order reaction. So how do we get the rate constant? Since we're also looking for the rate constant. Oh yeah, it's visible. So for the rate constant, let's just since the rate constant here, since it is an intrinsic property and the temperature was maintained all throughout the experiments, we just get any set of data. We just use any set of data from these experiments here. So let's say we want we will use experiment 1. We'll use experiment 1 as our reference, as the data that we'll use to get our rate constant. So remember, this is our reaction, right? Okay, it's hanging again. Oops. Okay guys, my camera is not really responsive, so bear with me. So we have here this reaction. So since in the experiment, the set of data from experiment 1, we already know this one, and this one, it is already given. So this is the unknown. Just rearrange the equation. So rate constant is therefore equal to the rate divided by that one, okay? Then we substitute our values. So I'll change my board, which is equal to, so in order to know the rate constant, the unit for the rate constant, we write the appropriate units for all the values. So for the rate, it is moles per liter second, or molar per second. So it will be 1.36 times 10 to the negative 4. If you see experiment 1 data, if you see experiment 1 data here, it's 1.36 times 10 to the negative 4. The unit is molar per second. And for hypochlorite, it's 0.0015 molar. And for iodide, it's also 0.0015 molar, if you can see. So therefore, the rate constant is, we cancel out all our values. So the units will now be 1.36 times 10 to the negative, so it's not 1.36. The answer is 60.44 per mole second. Okay, that's the unit. Or if you want to be very specific, it is also equal to 60.44 liter per mole second. Okay, that's the answer. That's for letter A. Now we already know for the rate constant, we can now find letter. We can now answer letter B. We can now answer letter B here. Now for letter B, the initial. For letter B, the initial values is this one. So it's 0.002. So we'll just use the rate law again. Since we already have our rate constant. We'll just use our rate law again. So rate is equals to 60.44 per molar second. Then substitute the values, which is 0.002 2 molar for hypochlorite and 5.0 times 10 to the negative 4 molar for iodide. So the answer is the rate will therefore be 6.044 times 10 to the negative 5. We'll cancel this out. Molar per second. Okay. So yeah, that's next. Now we will be discussing the integrated rate law. Okay, so don't go away. I'll be right back.
A few moments later.
So what we have shown so far in our in our rate laws that we have discussed is the effect is only the concentration component of the rate of the reaction. But since rate is a change, or the reaction rate is a change of a concentration at a certain time interval, or a change in time, or delta t. So we will integrate the time component in determining the rate of the reactions, and this is integrated by its namesake, the integrated rate law. Now, the integrated rate law varies on the overall order of the reaction. So the following equations are already shown here. Although the derivation, there is a discussion on how the final equations for the integrated rate laws of different reaction orders are obtained. We will not discuss it here in this video because it requires higher level of mathematics, particularly differential equations. So I'll leave that to your higher chemistry courses, particularly in physical chemistry. So there are different integrated rate laws. So we'll start for the integrated rate law for the zero order reaction, or in some books it's zeroth order reaction. So what does this mean? So by its same zero order of the reaction, the overall reaction order is 0. So all of the exponents of the reactants, all of the exponents of all of the reactants there is raised into 0. So for example, in this hypothetical reaction, a conversion of A into P, the A here is raised to the power of 0. So any number raised into 0 is 1. So that means what we will be left is K. And since K is a constant, that indicates that the rate is constant throughout the reaction. Now, if we try, this case is really, really rare, to be honest. This is a very, very rare case. However, I'll show this for the sake of everybody. Well, I have not known any reaction that occurs in the zero order, because that would be very, very weird. Now, however, there is a case, by the way, I'll correct myself. There is also a case, there are cases that the reaction is zero order. So, for example, the reaction of gaseous molecules on a solid surface, because when the solid surface is saturated with the gas molecules, the remaining gases kung ano lang tong ara sa solid surface, that is the one that will react to form products. So since the solid surface is already saturated, the other gaseous reactants that are not yet adhered to the solid cannot adhere anymore since it is fully occupied. Thus, no matter how great the concentration of the reactant you put there, it will not affect anything. It will not affect the rate of the reaction since the solid surface is already saturated. It's really, really hard to imagine, but I can't give an actual example of that because it's more complicated than it sounds. Okay. Anyway, so let's have our reaction here. Okay, so let's try graphing it. So if we graph a zero order of the reaction, so let's say the x-axis will be the time, and the x-axis will be the initial the concentration of the reactant A in our hypothetical reaction. If this is our initial reactant concentration, as time passes, it will decrease at a constant rate. Okay? So when you plot a concentration versus time graph, of the progress of a zero order reaction, you will get a perfectly linear. We'll get a linear graph, and the linear graph, if you remember our instantaneous reaction, if you remember our first part, the slope of this graph is our rate of the reaction. It's the overall rate of the reaction, right? And since the rate is constant, this is equal to the rate of the disappearance of your reactant for a zero order reaction. Okay. Again, my camera is responding slowly, so my apologies for that. So it would look something. It would look like that. Okay. Now. Now we will introduce a new concept, which is what we call the half-life. So half-life, by its name, is the time it will take for a substance or a reactant for its amount to decrease, for its amount to decrease by half, or for it to be reduced to half of its original amount, or in the language of chemical kinetics, the concentration. Now, for a zero order reaction, the half-life is given by these formulas. So, how was this derived? So, again, now remember that the rate of a zero order reaction is delta A over delta T. Okay. Now, initially, at T is equals to 0, at an initial reaction, the concentration of the reactant is given by this value, or our initial concentration. Now, after a certain time wherein it is already its half-life, by the definition of half-life, by the time it reaches its half-life, that means the original concentration of the reactant will now be 1/2 of its initial concentration. So remember that a change is final minus initial. So the rate is equals to final minus initial over, same goes with time. It's final minus initial. So since initial time is 0, so really any value subtracted by 0 is the same value itself. So we'll leave it at that. Okay. I substitute this relation to here, and you will get. Oh, sorry, I forgot the negative sign. We have a negative sign here since this is disappearance. So it's negative 1/2, or rather, negative here, 1/2 of A null, our initial concentration, minus the initial concentration, divided by T, divided by T 1/2. Okay, so since these are the same variable, so we can perform a subtraction operation with this directly. So 1/2 minus 1 is equals to negative 1/2 multiplied by the negative sign, which is negative 1. That will become okay, it's a bit slow, sorry. It will become 1/2 of A over T 1/2, right? Now remember that the rate is equal to the rate constant for the zero order reaction K. Okay, so T, your half-life is equals to, transpose it here, so equals to 1/2 of A over K, or A null. It's A null. Our initial concentration is divided by 2 multiplied by the rate constant. So that's how it was the equation was derived. Now, how about for a first order reaction? So now the first order of reaction, the rate of the reaction is directly proportional to the concentration of only one reactant. Since the overall rate is 1, that means ang summation sa constants nila should also be 1. So given this hypothetical reaction again, if this is the rate, this is the rate constant here. If this is the rate constant here, the rate law here, so this will be equal to the disappearance of A over disappearance of T. Now if the reaction monitoring started at the beginning of the reaction, so that means initial time is 0, therefore the integrated rate law, after doing higher level math of this, is equal to this one. So after time T, this is, so T here is the final, is ang aton nga final time. It's not actually the it's wrong to say final time, or time after the T is the time after certain value of seconds that you obtain the concentration of your reactant there. So the integrated rate law will now look like this. Okay, we're not concerned on how did it get from here to here, since it involves a higher level math. You just need to remember this for the integrated rate law. You just need to familiarize yourself with this, okay? That is for the first order reaction. Now let's let's show the graphical representation for a first order reaction, because we have shown for the zero order. It's quite simple. Now, it's not that simple when it comes to first order reactions. So let's consider this reaction, the first order decomposition of sulfurilyl chloride to sulfur dioxide and chlorine gas. Now we have the set of data here wherein the initial concentration, wherein the concentration of sulfurilyl chloride was monitored throughout the course of the reaction. So this is also one way of determining the reaction order. Actually, this is more common. This is what do you call this? This is the this is experimental. When you conduct experiments, this is actually much easier than the one that we shown for a simple rate law, for the fundamental concepts of rate law. The one particularly for the rate law, for determining the rate law of NO2 of nitrogen, the reaction between nitrite and ammonium ion in solution. This is actually much easier in practice to determine. So now we know that it's just first order. So from the first order reaction, we determine the rate constants. Okay, we now determine the rate constant. We're not given the rates. So how do we do that? Now, okay, for emphasis, we'll try to graph it as if it is a zero order reaction. Now, if you see it here, it is not quite linear. So we trace a trend line here, or if we average these data to form a straight line, it would look like this. And the r squared here, or this r squared is the coefficient of linear regression. Now the closer is the r squared to 1, the more linear the graph is. Okay, remember that the greater the the closer the r squared to 1, the linear the graph is. Now r squared here it's not exactly 1, but it is almost 1. Okay, which is already acceptable. So by practice, you will say that this is a zero order reaction. Okay, this is a zero order. By practice, if I collect this data and I plot it in the graph, I would say this is already a zero order reaction. I don't need to do a first order reaction, a first order kinetics here. I don't need to do a graph for a first order reaction here. So this is okay by me, but for emphasis again, let's try graphing it using a first, or as if it is a first order reaction. But before that, I will show you how did I get that graph. Okay. So we have our Excel here. That's the wrong set of data. Now this is the data for the problem here. So I've listed it down. So this is the number of mole. This is the time. I'll just disregard this one here. I'll just delete this one. Anyway, so this is the number of moles, this is the time. So to graph this out, you go to your Excel or to your spreadsheet. I'm using WPS Office because I'm not that rich. I still do not have the financial resources to buy legitimate to buy a licensed Microsoft Office software. So again, we'll go to insert. This is a series of charts we'd like to do. So what I would like to do is a scatter chart. So insert scatter chart. You just select here what do you want a scatter. So for me, what I did in the graph is I select this kind of scatter here, wherein the data points are shown and you trace a line over them. So We have it here. Insert. Right click on the chart. As you can see, the chart is blank. You right click on the chart. You go to select data. So we have this interface here. I hope you can see. Oh no, it's not visible. This is weird. So anyway, so you right click here. I hope it's not shown. Anyway, you right click, then you have your series. You add series, then you select your x values. Remember that your x values is your time, okay? Since your time is on the x-axis. Then you select your y values, which is the concentration, and insert. Voila, there you go. So okay, this is our chart. So if you see, it has a chart title. So I'll remove this one here. Now this can be modified. So we can change the chart title. Let's say reaction monitoring. We name it reaction monitoring. So we have that one here. Yep, we have it, that one. Then we can go to insert. I hope it's visible. Good. Or no, we go to chart tools. So chart tools, we click add chart element. You can see it there. We click to add chart element. Wait, so why is it not shown?
1 hour later.
Oh, okay. Good. So we go to we go to add chart element. Is it shown? Oh. Okay, you click add chart element, then you click axis title. So primary horizontal axis. So you name it, let's say this is time, which is seconds. Then you also need to have an axis title for your y-axis or your vertical axis. So obviously this is the sulfurilyl chloride concentration in mole per liter. So that's it. Also, you can set you can also set the axis range here. So you go to I don't know if Excel has this format. So you go to add chart element, then go to grid lines. So we have the primary measure. So then you go to more options. It will show you here. Then you click here. You go to horizontal value text box, or the horizontal axis. So that means for the time. For the axis here, you can limit for the axis again. Horizontal axis. Whoops. Ooh. You click this arrow here. Horizontal text box value axis. Click axis. Then you click again axis options. So this is the bound. So what will be your minimum and maximum limit? So since we have seen it here in our chart that none of them grazes in the 0.0060 value, so I can just set time. So if you can see, it does not graze the 1600 value. So I can change this to 1550, the maximum value. It will look like that. Now, since this is once this happens, usually the minimum value also changes automatically. So you have to set this to 0 first, and it will show you this. Okay. Now we can also what do you call this? You can also change the graduation with in the units. So the major units or the major graduations, it is shown here. So the graduations is by 200. So 200, 400, 600, so on and so forth. Let's say I want to change this to 50. So it will show you that. It already is here. Now, for the y-axis, since this is too high, since the graph is too high, I want to drag it down a notch. So I've observed that, if you have observed here, the data shows that over the course of the reaction, the sulfurilyl chloride did not change in value, did not, at this time interval, from 0 to 1,500 seconds, the sulfurilyl chloride did not decrease up to a value lower than 0.060 molar. So I can just, again, go edit this. So I click the chart, go to Chart Tools, click the Chart Tools there, click Add Chart Element, then I go to Grid Lines, again, more options. So, major grid line options, let's go to horizontal text value axis. Rather, vertical text value axis, there. So again, click axis. So, the minimum is 0, so I'll set the minimum to 0.06 since the lowest value that we have obtained is 0.0647, which is higher than 0.06. So I'll enter this, and it drags the graph down a notch, okay? So I'll just leave my maximum value be since it does not affect me in any way. And I'll just leave also the major grid lines be, okay? You can edit this if you want. Now, I have also noticed that the major grid lines for the vertical axis, for the y-axis was not shown. The major grid lines. So, what I do is go to Add Chart Element in the Chart Tools, Grid Lines. Then I click Primary Major Vertical Axis here. Primary Major Horizontal Axis. So it will give you that. Okay. And that's it. So that's how you plot a graph. Now, how to add the trend line? You click on the graph, right click on the graph, then you click Add Trend Line. It will give you that trend line. And that trend line can also be edited. So you right click on the trend line, here, right click, then select Format Trend Line. Now the trend line we have shown here, it could be an exponential, or a linear, a logarithmic, blah blah blah. Now, in our case, we just want a linear trend line. So it's already there. Then, you can display the equation of the trend line on the chart, which is shown here. So, if you remember your algebra, the trend line is, the equation of the trend line shown is the slope-intercept form, which is y is equals to mx plus b, wherein your m is your slope and your b is your y-intercept. So this is your slope here is negative 2 times 10 to the negative 5, and your y-intercept here is 0.0998. Okay, so I'll right click this again, Format Trend Line. Let's say I would like to change this color. So you right click your trend line, Format Trend Line, you go to Fill and Line. So the fill is, I cannot edit it. So you click on the line. Now you can change this into a solid line. So I'd like to change its color here to green. It would look like that. Also you can widen your trend line here, or you can expand your trend line. So I'll increase this to something like that, so that it is really visible. Anyway, so we have displayed equations, and we want to know the linearity of the trend of the graph by the r squared of the trend line. So if the r squared, so we click the we click the display r squared value on chart, and the r squared is displayed. So again, r squared, the maximum value of r squared will always be 1. Okay, there is no such thing as an r squared greater than 1. Now, if your coefficient of linear regression or your r squared is closer, is close to 1, that means it is almost linear. The closer the value of the r squared to 1, the linear the graph is. Okay, so if you see, this is almost 1. This is already good enough for a kinetic. This is actually good or acceptable for a set of kinetic data. So again, I can say that this is a zero order reaction, but it's stated there that it is a first order reaction. So let's try. Let's try showing our first order reaction now. Oh God, sala pang spelling ko ka-plotting. This is plotting, guys, ha. It's not plotting. That's a typographical error. Now let's try. Let's try plotting let's try plotting the natural logarithm of a concentration versus a time graph. Okay, and when we did that, it is perfectly linear. Look, it is 1, which is really unbelievable. Okay, even if you did experiments perfectly, remember in your errors there are still small random errors, we cannot identify the source, but it just occurs. Which will give some sort of affect both the accuracy of the and the precision of the data. Thus, we cannot get a perfectly accurate data. That is why I'm saying this is already good enough, because this is this is already accurate. Something like this is really unbelievable. Okay, i-claim ko na, a scientist ko joke. But someone who's a fanatic of science and who has experience also in conducting research, since in order to complete a bachelor's degree in chemistry, you need to complete you need to conduct a full-blown thesis. This is really unbelievable. Okay, guys, I just want to say this is really unbelievable. That you can obtain a perfect r squared. Oh my God, oh my God, joke. Either the experimenter, either the researcher who conducted the experiments has a perfectly deft hands that is not shaking by a perfectly deft, steady, and dexterous set of hands that does not shake or quiver from time to time, or this data is manipulated. Well, let's give some slack. Let's give Shwa some slack. I believe this is just a theoretical data. Let's give the author of the book where I got this example some slack. I mean, I believe this is just theoretical data. So just to conform with the first, or just to confirm that this is a perfectly first order reaction. This is for the sake of emphasizing the integrated rate law for a first order reaction. Anyway, so how did I get so how did I plot this data? Okay, so this is simple. This one's simple. Wait lang. Oops. Now, this one's pretty simple. So para hapos, for for simplicity's sake, I'll try I'll transfer this data. I'll transpose the data here. Yep. I'll transpose the concentration data for sulfurilyl chloride, and this is the time data here. So, how do we get the negative logarithm of something? The logarithm of something. So, if you can see in our Excel, this is real time. Good. So, you have your equal sign. Just type ln. So you click this function here. That when you click this, that means it returns the natural logarithm of the number. So that means when you click this function, I'll click this function. I know, dude. You double click that function, so it ln number. So you click a cell here that has a value. So since I would like to get the natural logarithm of sulfurilyl chloride, I'll click it down here. Then I'll click this cell here. So negative logarithm of this one, enter, and it will give you this value. So in order to but however, you need to get the natural logarithm of all of these values. So what I do here is I click this, I drag this, I left click the rightmost corner of the cell here, then drag this down up to where the data ends, and there it now gives you the the natural logarithm of each of these values here. So for this cell, ang ginkuha yung natural logarithm is this cell here, so on and so forth, and voila, you now have a set of logarithm values. So again, I constructed a chart for this. So sorry, XY scatter here. Right click on the blank chart, select data. For those who does not have Excel, I think it's add data or add series. So here for WPS, this is you click the plus sign here, icon here. Series X values, again, it is time. So you have your Series X values. You click this, then you select this data. You drag this down. Then for the Y values, it's important that you delete this one. You clear that box out. Then you select this value, drag it down, and enter. Then okay, you have it. Another problem that poses here is your x-axis here, or your time, is above. There is one way to circumvent that. So again, I click this axis values, this one, click it here, then so close it, right click, then format axis. So you go to you click number. No, not this one. You click labels. Okay, sorry. You click labels. So the label position is next to axis. So since this is negative values, diri siya nagposition. Okay, what does it mean when it says next to axis? Since the y-axis actually starts from the 0 value, right? So you click low, you click this next to axis, you click low, and it will drag it down lower here, the axis values. Okay, na. So again, I'll not put the labels, okay? I'll just put the label. So add chart element, more options, then click this one here. Sorry, sala. Add chart element again, axis title, primary horizontal axis. I'll just put time in seconds, and we have primary vertical axis. This is ln of the concentration of the sulfurilyl chloride. That's it. Again, same protocol. Right click on the graph, add trend line. Okay, right click again, format trend line. Display equation on the chart. Since it is perfectly linear, that means your trend line will perfectly coincide with the graph. That's it. Okay, now we have shown that there is a slope-intercept form here, which is y is equals to mx plus b. So this was actually derived from the integrated rate law. But how? But how? So, wait now. Guys, I'll erase my board. I'll be right back. So, remember that our integrated rate law is negative kt is equals to ln concentration of A at the time t divided by the concentration of, so for emphasis, I used the wrong pen. So this is ln k is equals to negative kt. It's like this, right? Now, remember our logarithmic laws that for the natural logarithm of a quotient, this one, is equal to the what do you call this? The difference between the natural logarithm of each of the values in the fraction bar. So this is equals to log x minus log y. Now we will separate our natural logarithms here in the same manner. So negative kt is equals to ln a t minus ln a null, or our initial concentration. Okay, transpose this one on the other side of the equation, and you will get, this is such a killer. And you will get this final equation, ln at, which, or in some books this is just ln a na lang ni siya, is equals to negative kt plus ln a null. So there, now this will be your equation of the line. So remember that y is equals to mx plus b. So your y therefore will be the negative logarithm of the concentration, and your x-axis will be your time, and your slope will be your negative k. Okay, it will be your negative k, and your y-intercept will be the negative logarithm of the the natural logarithm of the initial concentration of the reactant in the first order reaction. Okay, so going back here, since we have established that is the equation, therefore, since this is the slope is negative 0.003, that means your constant is, your rate constant is, your rate constant therefore will be 0.003 liter per mole, or per molar. Then, now, for a first order reaction, the half-life will be this one, okay? So how do we derive, so how was this obtained? again, going back to the integrated rate law of a first order reaction, going back to the integrated rate law of the first order reaction, again, my camera is not responsive. It's responding slowly, so forgive me, guys. So again, the T here will now be a T1/2, or our half-life, okay? Therefore, since half-life siya, therefore, as it reaches its half-life, when it reaches its half-life, the concentration of the reactant will now be 1/2 of its initial or original concentration. It's not visible again. Yep, I hope you can see. There it is. Okay, so we substitute these values. I'll move my camera. So that is negative KT1/2 is equals to ln one-half A0 divided by A0. So they will cancel out with each other. What you'll left is ln natural logarithm of 1/2. Okay. Then we transpose the negative sign here. So since this is a multiplication, when you transfer the negative sign here, this is equivalent to -1. So when you transfer it here, it will becomes divided by all over -1, and any number divided by -1 will become a negative equivalent of its original value, right? So your reaction, your equation therefore will be transformed into, I did not delete this, sorry, will be transformed into KT1/2 KT sub 1/2 is equals to negative ln 1/2. Right? Now we know that, or we can say, sige 1/2 na lang. Now we know that in our logarithmic laws that if a logarithm of something is multiplied by a constant, this is equals to the logarithm of the value raised to that constant. So we will apply that logarithmic law. It's equals to ln 1/2 over -1. Right? Since this is equivalent to -1. And remember that any value raised to any number raised to a negative value, or in this case -1, is equal to the reciprocal of it. Raised to the negative value is equal to the reciprocal of the value raised to the positive equivalent of this negative value here. So, for example, if x is raised to -1, therefore it is equals to 1 over x raised to the power of 1, or simply 1 over x. So therefore, this one will be transformed into ln 1 over 1/2. And 1 over 1/2 is equals to 2. So it will be, so therefore, KT1/2 is equals to ln 2. Thus, transpose K to the other side. This will be half-life is equals to ln 2 divided by its rate constant. Okay. Now, in other textbooks, particularly in general chemistry textbooks, they show this as 0.693 divided by the rate constant, because ln natural logarithm of 2 is equal to 0.693. There's actually a long list of values here along list of values here, but they just rounded off to 0.693. If you're the meticulous one, you will not. If you get the meticulous one, you will be obsessed if you round this off to just 0.693. So you can just use ln 2, the natural logarithm of 2 divided by the rate constant. Now, let's go naman to the integrated rate law of the second order reaction. But before that, let's try an example for solving the half-life. The gas phase decomposition of sulfonyl chloride is in first order. So the same example. So we know that the half-life is 2.3 times 10 to the negative 5 seconds. What is the rate constant at this temperature? So,
One eternity later.
So we go back here. Okay. So we go back here. T. So we go back here. So we know this one. We just transpose. So K is equals to ln 2 over T 1/2. So it is equals to, the value is ln 2 divided by 2.3 times 10 to the negative 5 seconds. So this is equals to divided by 2.3 times 10 to the negative 5. 2 times 3 times 10 to the 5th. Galit na. So it's equals to 3.014 times 10 to the negative 6 liter per mole, or per molar. So that's the final answer. Hello guys, I just paused the video just to take off my mask. Sorry about that. I'm just alone here in the office. So if you're thinking that I'm breaching the minimum health guidelines, I'm not. I'm the only one here in the office right now. So now if you notice, we have seen that the half-life of the reaction is not dependent. For the expression of half-life, there is no the initial concentration of the reactant is not included. What does that mean? That means that for a first order reaction, the half-life the half-life will be the same irregardless of the initial concentration of the reactant. So we can say that the half-life is also an intrinsic property because it does not depend on the amount of the reactant present. The amount of the reactant or the amount of the substance. Now, this is pretty easy if you're already given half-life. What if you're not? Let's say you're just given video capture. Let's say you're just given a certain amount of time, which is time t, and you're only given the initial. You've already determined the initial reactant concentration. However, you know this first order reaction, but you want to know how much of it will remain. We don't know the half-life. So let's say we just this is not the half-life. So how do we get from the initial concentration? How do we get the amount of the concentration of the reactant will remain. So you have, let's go back to the integrated rate law. Negative Kt is equals to ln A over A null, or the initial concentration. Now, in order to, you cannot just simply move this here, because you still have a function here, the natural logarithm. Now, in our logarithmic laws, the when the logarithm of a value base to a certain number, name A here, is an exponent to its base. So that means a certain value, let's say a certain number A, is raised to the logarithm of x base A. That means they will cancel each other out. What you'll get is this is equal to the value of whose logarithmic function base of a certain number you get. Okay, I hope you get it. Okay, if I hope I explained it correctly. So remember that the natural logarithm is of a certain value x is equals to the logarithm of x base E, or the natural or what they call in mathematics the natural number. I don't know how is that called. So therefore, in order for you to get the value of the actual value of x, you need to raise this to the natural value. So E raised to the natural logarithm of x is equals to x. We will apply the same logarithmic property here. So in our rate law, so on the one side of the equation, we just make it an exponent to raise it to the natural logarithm. Okay, and what you do on one side of the equation, you do on the other side. Okay, so this will become A null over A over A null, right? So this will be negative E raised to the negative. This will be a natural number raised to the power of Kt. So transpose on the other side. Thus, at time t, at the given certain value of time, at the given certain time, the concentration of the reactant after a time interval t is equals to A null is equals to the initial concentration multiplied by the natural number raised to the power of negative k, or its rate constant, multiplied by the time. Okay, so you just substitute. So that's it. Okay, so now let's proceed for a second order reaction. Now for a second order reaction, now we have shown that we have seen that for the example on our first determination of rate law, particularly the reaction between ammonium and nitrate in the one that we have previously discussed, the overall rate of the reaction is 2. Now there are two cases of a second order reaction. Now we will only discuss the integrated rate law for the first case. We will leave the second case. The second case is the one similar to the example that we have discussed when we discussed the basics of the rate law. So the first case is only one reactant participates. For example, in this reaction here, since it's a second order reaction, the rate law here is K is rate constant multiplied by the concentration of the reactant raised to the power of 2. This is the first case of second order reaction. Now, the integrated rate law for that will be this one. This is much simpler than the integrated first law. So, later, what will be the equation of the line? We'll see that later on. Now, let's consider this second order decomposition of nitrogen dioxide. So let's again plot a graph. So to emphasize, we tried it with the first. We tried plotting it as if it is a first order, a zero order, and a second order. If you can see, the lines are not linear. You can get the r squared. It will still show you the same value. Now, for the second order reaction, now the equation of the line will be in its slope-intercept form. You just transpose this original equation. You just transpose this one to the other side. It will give you this one. So 1 over A is equals to KT plus 1 over A null, or the initial concentration of the reactant. So this will be your Y for the slope-intercept form. This will be your Y. Your rate constant here will now be your slope, not the negative value of the rate constant. So this will be your X, and the whole thing here will be your Y-intercept. Okay? So how did I plot this graph? So this is just quick. Oops, erase all inks and slides. This will just be quick. And oops. So it would look like that. Oops. So here, delete. So how did I get this one here? So I'll delete this one just to show you. So again, equal to, you press equal sign. So that means it will give you the answer to whatever operation you're going to do. 1 over, since what we're looking is 1 over the initial concentration. So 1 over, you click this value, you click the cell, then it will give you the 1 over the initial concentration of nitrogen, NO2, or nitrogen dioxide. Again, just like what we did in the plotting the first order reaction, plotting the graph for a first order reaction, we left click on the right hand corner here. It should show a plot. Remember, guys, that it should show a plus sign. Then you drag it down to the rest of the data. Then what you will get the corresponding 1 over concentration of this specific reactant. So, for example, this value is 1 over the this cell that contains the concentration of your nitrogen dioxide. So again, we'll plot the chart. So go to insert, find this one here, the insert scatter. You can choose any, but I prefer this one, the scatter with smooth lines and markers. So it indicates the data points, and at the same time it traces the data points. So it looks like that here. Then select data, click it here, X values, the time, Y values. Make sure to delete this one. To delete this one here, you cannot just do backspace. You call this highlight it, then click. You press the delete button in your keyboard. Then you click. Oh, sorry, wrong set of data. You click. You drag down this set of data here, and okay, you'll get this one. Again, for emphasis, we add trendline. We format the trend line. We show the equation and the r-squared of the chart. That's it. Okay, so therefore, the r-squared, therefore, the rate constant now will be, our rate constant will simply be this one. This will now be our rate constant. This will be our K. Okay? I hope you get it. Now, for the half-life of a reactant in a second order reaction will now be this one. Excuse me guys, I'm gonna blow my nose. So how is this obtained? So we go back. Sorry, wala siya napakita. This is the half-life, okay? Again, this is the half-life for a second order reaction. So how is this obtained? We go back to the equation for a second order reaction. Which is equals to 1 over minus 1 over, or 1 over A na lang ni siya. Now, we know that, now for half-life, again, if this is your half-life, if T is your half-life, then this one here, the concentration of the reactant at time T will be 1/2 of its initial concentration. So we substitute is equals to 1 over 1/2 A null is equals to 1 over A null. Minus, dali. 1 over A null. Right? So this one, since 1 over 1/2 will be transposed here, this is equals to 2. Therefore, wait lang. I need another whiteboard. Therefore, the integrated second law can be transformed into this one. So 2 over A null minus 1 over A null. Remember the properties of your fractions, that if an addition and subtraction operator, subtraction operation is done between two fractions of the same denominator, you can just copy the denominator, then you just subtract the numerator directly, okay? So we will use that property here. So, since 2 minus 1 is equals to 1, so 1 over A null. Therefore, manipulation of this equation will yield to you that T, the half-life is equals to 1 over the rate constant that multiplied with the initial concentration of the reaction. Okay. So just like in the just like for the half-life of zero order reaction, the half-life is also dependent. The half-life for a second order reaction, first case, is also dependent on the initial amount of, or initial concentration of the reaction. Or the reactant rather. So now how do we determine whether the reaction is 0, first or second order? So let's have an example taken from Zumdahl and colleagues, which where in 1,3-butadiene, which is this one here, undergoes dimerization reaction to form 1,5-octadiene according to this chemical equation. Now, given this chemical data below, we'll determine the order of the reaction and its corresponding rate constant. So how do we do that? We're just given this one here. We're not given the rate of the reaction. It's like the data that we've seen for the integrated for the integrated first and second order reaction. Integrated rate law rather of the first and second order reaction. So this is just trial and error. This is just trial and error. So what we actually do here is this one here. So you just make a graph for zero first and second order and see where it fits the most, or where it exhibits the greater linearity. Now for here, I have not done for the zero order reaction because it's not saying I know it in my heart. I mean, as I've said, a zero order reaction or zeroth order reaction is very, very rare. It's so rare. It does not usually occur in reactions in just simple conditions such as this one. So this reaction being a zero order is out. So we just choose if it's a first order or a second order reaction. So I plotted it using a first order, as if it is a first order. So I got the negative logarithm of each of the concentrations, natural logarithm of each of the concentrations. I plotted it. I have this equation here, and this is the r squared. This is actually a bad r squared. That means that this is not linear. So that means this is a second order reaction. But scientists as we are, we want to make sure. So we plot the data for a second order reaction, and by plotting the data for a second order reaction. So sorry, I forgot to put the axis title here. This is this is actually an acceptable and actually a really, really good r squared. This is almost 1. That means the data collection was really, the experiments were done perfectly. This is actually a really, really good set of data. I commend to whoever collected this data for the kinetic data for this reaction. So here we plotted it using a second, as if it is a second order. Now we compared the r squared between the first and the second order. Obviously, this has a greater r squared. This r squared is closer to 1. That means that the reaction is actually the dimerization of 1,3-butadiene is actually a second order reaction. Well, actually, this is known as second order reaction. The reason why it is second order, it will be explained in your higher chemistry courses, because this is a reaction. This is a reaction of organic compounds. So this will be discussed in organic chemistry. And I hope I stay here, and I hope you still continue down this program. Still continue the BS chemistry program, for you to know this kinds of reaction. Hopefully, anyway. So now, based on the data that we have gathered, that the reaction is a second order reaction. Now, let's try the importance of collecting more kinetic data for our reaction. Now, this is not only applicable to kinetic data, but also in any experimental data that you'll encounter in chemistry. It's the more data that you collect, the greater the accuracy of your results. Okay, this is also applicable to determining the order of the reaction using the integrated rate law. So, for example, we're given this 5 set of data here. We plot this using the first and the second order, and if you see in the data, although their r squared is close to value, obviously this one here, this one is a second. This one here, the second order, the the graph for the second order reaction is greater compared to the r squared of this graph for the first order reaction here. So you can say that although they are really close to value, you can't tell if it's a first order or a second order because their linearity is really the same. But since they have a very, very small difference here, you will say that, this is a second order reaction. However, if you go along the line of the reaction, of the progress of the reaction, so that, for example, in this set of data here, for this hypothetical reaction, you collect more and more data as the reaction progresses. So you go beyond 240 seconds. So you go from 240 until 1,800 seconds here, and you plot you plot the data for a first order and a second order of the reaction here. If you can see, if you plot all of this data into that for a first order reaction, its r is now getting nearer to 1. So it is now very, very close to linearity. Compare this with a second order reaction that it's not that linear. Even if you do not look the graph, if you do not get the r squared, if you just look at the trend line versus the graph itself, this is quite far from a linear value compared to a first order reaction. Thus, that means this reaction here is a first order reaction. This now emphasizes the importance of collecting more kinetic data for your reaction kinetics as you go along, as you monitor the progress of the reaction. So that means you have to monitor the progress of the reaction a little longer. You just do not set on a short span of time. You prolong the reaction as much as possible so that you can get a more accurate data. Okay, so now in summary, to summarize our integrated rate laws. So for the zero order reaction, the integrated rate, the rate law will be this one. So that means it will be constant all throughout the reaction. Its integrated rate law for a zero order will be this one. Transpose this one here, you'll get the linear equation. So this will be your what do you call this? This will be your slope, so on and so forth. This one. So again, I would like to emphasize that for only a first order reaction, the half-life is equal to the half-life is not dependent on the initial concentration of the reaction for a first order, unlike for the zero and the second order of the reaction. Okay, so this is the end of my this is the end for the part 2 of our reaction kinetics. I hope you understand what I'm saying. I hope you learn. I hope you understand what I'm saying. And again, just do practice. Do not rely on my videos alone. You also read not only the modules but the ebooks that I've sent to you. Okay, so that's it. See you